Today we are looking at radioactive isotopes and half-life. Half-life is the rate of decay of an isotope. Don't forget that isotopes are typically very large nuclei that have become unstable because their neutrons and protons are so far apart that they begin to break down, also known as decaying. Half-life is the rate at which each of these radioactive isotopes decays. Okay, so what is a radioactive isotope? Again, it's an isotope of an atom whose nucleus has gotten very large. The protons and neutrons are very spread out, making it unstable, and so they decay or break down into other elements. Radioactive elements are unstable. They decay and change into different elements over time. We talked about that. They emit either an alpha, beta, or gamma. The nucleus does, and it turns into other elements. Not all elements are radioactive, and it's important to note, look at the bottom. So for uranium-238, they know for a fact that the half-life of uranium-238 is 4.5 billion years. So this means that all elements of uranium-238 or isotopes are going to decay at that rate. Potassium-40 decays at a rate of 1.25 billion years. Its half-life, and so they know that that is its rate of decay. And carbon-14, its half-life is 5,730 years, and they know that that is the rate at which carbon-14 is going to decay. So when a nuclei is unstable, that is also called radioactivity. It results in the emission of either of one of these three things being released or emitted from the nucleus, an alpha particle, a beta particle, or a gamma, and then it decays into a new element. Again, this is their symbols. That's what they look like. So there's some medical applications of half-life. So if you take iodine-131, its half-life is 8.1 days, and so they prescribe that to treat the thyroid. So if they know that the half-life is 8.1 days, then they know that it's 16.2 days that it's going to stay in your body. So at half that time, it's going to be 8.1 days, and then half of that would be 4.5 days, and so on. Iron 59 has a half-life of 45.1 days, and that treats your red blood cells. Strontium 87 has a half-life of 2.8 hours, and that treats your bones. Technetium 99 has a half-life of 6.0 hours, and that's used for the heart. And sodium 24 has a half-life of 14.8 hours, and that's used for your circulatory system. So when doctors prescribe medications to individuals like ourselves, they know how long the half-life is. They know exactly how long that medication is going to stay in your body. And if you're taking more than one medication at a time, then knowing the half-life and how long each one of those is going to stay in your body becomes critical to what they prescribe you. So the rate of radioactive decay is called half-life, and that measures the rate. Half-life is equal to the time required for half of the radioactive sample to decay. The half-life for a radioactive element is constant, so each isotope out there has its own half-life or time that it takes to decay. For example, strontium 90 has a half-life of 29 years. So if you have 10 grams of strontium right now today, in 29 years or half of its life, you're going to have 5 grams remaining. Another half-life or another 29 years, you would have 2.5 grams remaining. So it's important that you know how to read a decay curve. You will have decay curves on your test, and it shows the rate of decay for radioactive elements, and it shows that relationship between half-life, or the amount of time that goes by, and the percentage of the original substance that is remaining. So let's go ahead and look at our first curve here. So you can see on the side that it tells you the percentage of how much strontium there is, and the bottom is half-lives. At 0, you can tell that you have 100% of the sample that you were given, so that's 10 grams. At 1 half-life, you will have 50% of that 10 grams remaining, so you will have 5 grams. At 2 half-lives, you will have 25% of that sample remaining, so you would have 2.50 grams left. And at 3 half-lives, you would have 12.5% of the sample remaining, so you would have 1.25 grams. And if you wanted to do 4 half-lives, you would have 6.25% remaining, and so 1.25 divided by 2 would be maybe 75. I don't know, you have to do the math, but that's how much would be remaining after 4 half-lives. So these charts are very easy to read. You start at 0 half-life with 100% of the sample, and in this case it was 10 grams. At 1 half-life, you have 50% remaining, or 5 grams. At 2 half-lives, you have 2.50, or 25% remaining. And at 3 half-lives, you have 1.25 grams, or 12.5% remaining. And you'll notice that each one of these is divided by 2 because half is represented by 2. All right, here's some facts to remember. The half-life of an element is the time it takes for half of the material you started with to decay, and each element has its own half-life. Each element decays into a new element. So, for example, carbon-14 decays into nitrogen-14. And we'll look at that in just a second. And finally, the last thing to remember is the half-life of each element is constant. It's like a clock keeping perfect time. Okay, so if we start here, we have a blue grid, and that blue represents carbon-14. Each time you click on it, 1 half-life goes by and turns red to represent nitrogen-14. If you look at your chart, you can see at the half-life of 0, no time has gone by. So you still have 100% of blue, carbon-14, 0% of red, nitrogen-14, and there's no ratio. But let's see what happens when you click. So at 1 half-life, you have 50% of blue, carbon-14 remaining, and 50% of red, nitrogen-14 remaining. So you're looking at basically a ratio of 1 to 1 here at 1 half-life. At 2 half-lives, you only have 25% of the blue carbon-14 remaining and 75% of the red nitrogen-14. So now you're looking at a ratio of about 1 carbon-14 to 3 nitrogen-14. After 3 half-lives, you have only 12.5% of carbon-14 remaining, the blue, and you have 87.5% of red nitrogen-14 remaining. And so now you're looking at a ratio of about 1 carbon-14 to 7 red nitrogen-14. So after 1 half-life, there's half of the original sample left. That is why you are always going to divide by 2 when we start doing the calculations. After 2 half-lives, there will be half of the half left, or either 1/4 of the original sample, and so on. That is not my noise. So in order to solve these useful half problems, a table like the one below is useful, and we will create a chart every time we work half-life calculations. So let's look at this particular example. If we have 40 grams of an original sample of radium-226 to begin with, how much is left after 8,100 years? So the way the chart works is you put in half-life in the upper left and the mass in what is going to be for the upper right. So at 0 half-life, no time has gone by, so you still have 100% of that original 40 grams left. At 1 half-life, you only have 50% remaining, and the time that has gone by is 1,620 years. So that tells me that the half-life of radium-226 is 1,620 years, and at 1 half-life, you only have half the sample left. So you divided 40 by 2 to get to half the sample. At 2 half-lives, you only have 25% of the original 40 grams left. 3,240 years have gone by, and I know that because if the half-life is 1620 and you've had 2 half-lives, that's 3,240. And so what's going to be left here? Well, if you've got 20 grams and you divide it by 2 to represent a half-life, you're going to have 10 grams remaining at the end of 2 half-lives. If you have 3 half-lives, then you're only going to have 12.5% of the original 40 grams remaining. You're going to have 4860 years that have gone by. Again, that's the half-life multiplied times 3. That's 3 half-lives. And you're only going to have 5 grams remaining. After 4 half-lives, you're going to have 6.25% left, and your time that has gone by is going to be your half-life times 4, so 6,480 years have gone by. And if we had 5 grams remaining here, then we're only going to have 2.5 remaining here. And I don't know if you can see the bottom of this screen. I'm going to move it. So at 5 half-lives, you only have 3.125% of the 40 grams remaining. You have 8,100 years that have gone by, and that's what it asks us for. How much is left after 8,100 years? And so it's going to be 2.5 grams. So if you have 40 grams of an original substance of radium-226, there is going to be 2.5 grams left after 8,100 years. And all I'm doing there is dividing by 2 to get down to the years, and I took my half-life that they gave me, 1,620 years, and multiplied it times each half-life to get the number of years. And then when I got to 8,100, I knew that 5 half-lives had gone by, and I had divided 40 by 2 5 times to get 1.25 grams left. So let's look at this decay of carbon-14. You have at 0 half-lives across the bottom, you have 100% remaining of the sample, so there's 10 grams. At 1 half-life, you have 50% remaining at 5.0 grams. Notice that you're dividing by 2 there. At 2 half-lives, you're going to have 25% remaining at and you'll have 2.50 grams left. And at 3 half-lives, you're going to have 12.5% remaining and 1.25 grams remaining. So after 3 half-lives, you would have 1.25 grams out of 10 remaining. Again, this just shows you 50% you only have 50% left at 1 half-life, 25% left at 2 half-lives, and 12.5% left at 3 half-lives. Okay, so if you have 100 grams of radioactive carbon-14, the half-life is 5730 years. So after 1 half-life, 100 divided by 2 is 50. So how many grams are going to be left after 2 half-lives? So 1 half-life, you got 50 grams left. So at 2 half-lives, you would have 25 grams left. And that's it for our half-life or rate of radioactive decay PowerPoint. If you have any questions, please let me know. I'll be happy to help you.